which will be on Friday. So what times you prefer? 5 to it will be in between 5 to 6:30. What times you prefer?
Sir, 6 o'clock, sir, because 5:30 our class ends, sir.
Okay, 6 o'clock, 6 to
Yes,
6:30. Okay.
yes,
Quiz you generally waiting half an hour or 25 minutes. I'll check it.
yes,
And
sir, half an hour. Yes,
we will check it. If 10 questions are there, there can maybe less. Right.
yes. So we'll be
So
having
if
10 questions, sir.
this time we are planning to give 10 questions. Next time maybe 20 questions. Right.
Yes,
This time it will be, there'll be 10 questions, but numericals should be there. Right. And numericals as well as the non-numericals would be there. Right. But MCQ types. Right. 10 marks, 10 questions will be there. Right. So keeping your time, it is noting it. It is 6 p.m. Okay, Friday 6 p.m.
yes,
Is it okay, na?
yes, sir.
So Friday 6 p.m. So Friday, which date it is? Friday?
Sir, 11th.
Friday it is 11th. 11th to 6 p.m. Just a minute. Just confirming the other branch. Let me take her consent. हाँ सोमा 6 बजे ठीक है ना? 6 to 6:30 के अंदर ठीक है ना? हाँ, हम लोग देख लेंगे 25 मिनट से 30 मिनट हम लोग देंगे, देख लेंगे बाद में। अभी तो 6 बजे शुरू करेंगे, ठीक है? 6 पे फ्राइडे 6 PM, ठीक है? नोट कर लेना, अनाउंस कर देना, ठीक है? ओके। So it is confirmed now 6 PM. So but then you will note it and inform others, those who are absent. Okay, just a
Yes.
minute. बोलो। सुंदर फैमिली का नहीं ना, একটু দাঁড়ানো কি আর প্রাইভেট করেন না, হ্যাঁ অনেক দেশে আমার তো দাওয়া করে আসতে পারছেন, তোমাদের হোয়াটসঅ্যাপে আমাদের এসছে কি না, আমাদের সবাই the slide is visible to you?
Yes, sir.
Okay. So last times we were discussing the signal attenuations. We have discussed signal attenuations. We have seen power is attenuated after a certain distance, and we have seen this that relation also important. We have seen this P input. We have seen it alpha, that is attenuation. You can determine 10 by L log of P input by P output, that we have seen it. And the causes, we have seen it because of mainly absorption scattering, but other than also those things are losses are there. Now under absorptions, we have seen it. There may be due to atomic defects, maybe extrinsic absorptions, maybe intrinsic absorptions, right? Those things we have seen it. And in case of scattering, mainly absorption scattering, under scattering we have seen this, the Rayleigh scattering, most there are different types of scatterings are there. The Rayleigh scattering is most important in optical fibers. When refractive index variation is here, and that variation is that variation occurs within a distance, a very small distance of the lambda, and that will be due to, say, density variations, structural defects, etc. So these will result the density, these will result of refractive index variations, and in turn the Rayleigh scattering occurs. And Rayleigh scattering, it is characteristic inversely proportional to lambda to the power 4. Right, that is the important things. Also, we have seen the radiative loss, like bending loss. Bending can be micro bending, can be macro bendings. In case of macro bending, radius of curvature is quite large compared to the radius of fibers. And in case of micro bending, it is the order. They are almost same. So bending is there. So these are to be taken out, and so bent fiber, this number of modes will be less compared to the straight fiber, because some of the modes they will be radiated out. And in case of micro bending, we have seen this some compressible jacket can be used to avoid that loss. Also, you can have losses due to core and cladding, different losses due to different attenuation coefficients, alpha 1, alpha 2, and that will be different for SI fiber and GI fiber. Well, this is all about this the signal attenuation, signal attenuation or attenuation mechanisms. Now we'll consider the signal distortion. So it's quite clear now what is signal attenuation, what is signal distortion. Signal distortion, here it is, if you launch a pulse, last time mentioned, then that pulse shape will be changed. Pulse shape will be changed. A particular pulse, if you launch it, either that will be broadened or be narrowing, right? You see it here, if this pulse is launched, then after the fiber, a certain distance, the pulse shape, generally it is broadened. Because of mainly the dispersion effect, and that is called pulse broadening. So pulse broadening effect because of generally dispersion effects. Not necessarily always there will be pulse broadenings. There can be reverse phenomena also. Phenomena might occur also. That is the because of Carr effect or the nonlinear effect, nonlinearity, and that times you see pulse narrowing will result. Right, pulse narrowing instead of broadening, there will be pulse narrowing will result. Right, I mean many frequencies will be generated because of nonlinearity, and also the concept of soliton is there. If you have time, I can mention something about soliton and this nonlinearity and this dispersion. If these two are balanced, then a new generation optical fiber would be created. That is the, I mean, already established, not in the fully in the market, but already it is established in different labs. That is soliton systems in optical fiber. Well, let us focus on these things, pulse broadening mechanism, which is common in all type of fibers. So in that case, you see it here, if the launch the very narrow pulses, then after a certain distance, pulse shape will be broadened. And even if you increase the distance, then see it, they will be overlap in such a way that you'll not be able to recognize the original pulse. So that will severely affect the data rate or bandwidth of the fiber, right? And this is because of the this occurs because of the dispersion effect, right? In fact, we have seen this the group velocity, phase velocity within the fiber generally modulated light propagates. So you have to consider the group velocity. That group velocity is a function of lambda, right? Wave velocity, we have seen this A sin omega t plus single frequency is there, but generally fiber medium it is not. I mean, fiber medium to some extent dispersion is dispersive in nature. So and light also, it is not strictly monochromatic. Polychromatic light is there. I mean, quasi monochromatic light is there. So some dispersion effect will be there, and because of these things, the pulse broadening will result, right? Because of these dispersion effects, that we have seen very similar to prism. Okay, let you see. You see this dispersion effect, maybe two types. It can be intramodal dispersion effect. It can be intermodal dispersion effect, right? So what I mentioned just now, the group velocity is a function of lambda, right? That will velocity will be different for different spectral components. That will result the dispersion effect, right? So this dispersion effect actually can be two types. It can be intermodal dispersion, it can be intramodal dispersion. And this dispersion effect, intramodal dispersion effect, it is dominant in case of single mode fiber, and in case of intermodal dispersion, this will dominate in case of multimode fiber. Well, in multimode fiber, actually, you can have also intramodal dispersion, but their contribution very less compared to intermodal dispersion, right? So these are the two dispersion effects that will cause the pulse broadening within the fibers, SI fibers. GI fibers also same things are there, little bit different. You can see it. So this will result the pulse broadening. Pulse broadening, right? And now if you consider the intramodal dispersion, the causes actually this can be due to two factors. It can be due to material dispersion. It can be due to object dispersions. Material dispersion, similar to chromatic dispersion, probably I've heard. Chromatic dispersion means where if the refractive index it is function of lambda, then it varies with lambda, then the material dispersion occurs, and that will result the pulse broadening, right? So this is lambda means if you use LED sources and LED sources, then situation will be worst in case of the LED sources, because large value of spectral width is delta lambda. So it is large means more dispersion effect will be there. But LED it is almost monochromatic. Towards monochromatic, not perfectly monochromatic, but coherence is there. So because of these things, delta lambda is very narrow. So this dispersion will be less. We'll see in details of the quantitative and qualitative descriptions of the things. And next you see waveguide dispersions. Another factor is there that will also a factor for intramodal dispersions, intramodal dispersion, waveguide dispersions. And here you see single mode fiber. These two are the factors that will cause dispersion in single mode fiber. So in single mode fiber, if you consider the fundamental mode HE11 mode or LP11 mode, or you can say, in this mode it has almost Gaussian distribution, Gaussian nature, right? And the field tail is here and on both sides of the core, right? And if you think about 80% of the power flows within the core and 20% power in the floor, power flow will be there in the cladding regions, right? And you see, since refractive index varies differently, here it is N1, here it is N2, right? N2, and N equal to C by V. C the velocity of light in vacuum, V the velocity of light in the medium constant. So if refractive index is more here, refractive is more, it means velocity is less, right? And velocity is more means refractive index is less, right? Velocity less means refractive index will be more. So variation of velocity is there because of these things, the spectral components, they will have different delay will be there, and that will result the waveguide dispersions, right? So this is the waveguide dispersion because of the different amount of light propagate in the core and the clad. And in this case, actually, you'll see the propagation constant beta. It depends upon the fiber parameters like A and A by D. So that is actually A by lambda, function of A by lambda. So in this case, propagation constant is a function of A by lambda. Then waveguide dispersion occurs, right? So these are the different dispersion effects. And in case of multimode fiber, we'll see intermodal dispersion is here. And this time the many modes will be there. A single mode, many modes will be there. And these modes, they will have different group velocities. So they will arrive at the other end at different instants of time. So that will result the pulse broadening in case of fibers. We'll see it in details of all those things. So let us calculate this dispersion effect or the pulse broadening in each cases. In general, you can calculate also as a whole by calculating the group delay per particular distance, right? Dispersion effect can be, or pulse broadening amount of pulse protein can be calculated if you calculate the group delay, right? Group delay. So let us consider right group delay for these to calculate the pulse protein. Suppose in a fiber in general, this is the general relations. But individual also can calculate material dispersion, object dispersion, and intermodal dispersion separately. That will see it. Let us say all the things are combined together, so now can calculate the amount of pulse spread. So to calculate this group delay, actually you have to assume these things are there. If you assume all the modes when you launch light into the fiber, then energy will be distributed among different modes, and all the modes you assume it here. All the modes are equally excited, and each mode contains all the spectral components that the source emits. Right. I told you, even if you consider laser source, it's single lines, some spread is there. Some spread is there, delta lambda is there. So delta lambda is there also. Right. So some spectral width is there. So the mode contains, each mode contains all the spectral components that the source emits. So with these assumptions, next you can calculate the group delay. Group delay per unit length. If this is the group delay, if the distance of propagation, if you consider L, then group delay per unit length, that is actually velocity s equal to vt 1 upon vg, right? Group velocity, and that group velocity, it is actually 1 by c d beta upon dk. We have seen this phase velocity, group velocity d omega upon dk. We have seen it. Remember, in case of in a mediums, particular mediums, you can consider, if you consider particular index, then actually it will be that Vg, these things we have seen earlier, phase velocity, group velocity, right? So in a medium, it will be actually d omega upon d beta. So from that, you can consider this this d beta 1 upon c d beta upon dk. Right, this can be written from these relations. You can write, if you convert into beta, then it will be 1 upon c d beta upon dk. Right, you can have it. Actually, d omega upon dk into d beta into d beta upon dk. Right. So d beta upon dk. In this way, also you can write it. And 1 upon c. Vg equal to d omega upon dk. Oh no, in a mediums, actually you have to write, not these ones, d omega upon d beta. Vg, that is actually d omega upon d beta. So that is d omega upon dk into dk upon d beta. Right. And this in a medium you can consider c, so it is c, right? And so 1 upon Vg equal to 1 upon c into d beta upon dk. That's what it is here. You see 1 upon c d beta upon dk, 1 upon Vg. So that is actually 1 upon c d beta in terms of lambda. Also you can write it d beta by d lambda mathematically. In lambda variation, if you consider d beta by d lambda into d lambda by dk. And you see d beta by d lambda, right? And this d lambda upon dk, this can be calculated like this: k proportional constant k 2 pi by lambda. So if you just differentiate with respect to lambda, that is dk upon d lambda. So that means it is minus 2 pi lambda square. Minus 2 pi lambda square. You see it. Not too difficult, just using the differentiations. Okay. So next, you see, if the source, if you have a source that has spectral width of delta lambda, spectral width. Then you see, and you know, these the spectral components just I mentioned, the spectral components, they will move with the different velocities. So they will arrive at different state of times. So that will result, that will give the dispersion effect. And different delays will be there for different spectral components, right? So if you calculate that delay for different spectral components, that is actually you see DTG delays per unit wavelengths. The delay per unit wavelengths will be DTG by d lambda, right, per unit wavelengths. And so if the source, it has a spectral width of delta lambda, then total delay will be delay per unit wavelength times the total spectral width. So that is actually the group delay. Tau G group delay, the delay spread, that is actually amount of pulse spread, right? How much pulse, how much spread will be there, that is actually tau G. This tau G, then it is dTg by d lambda times delta lambda. Now if you just have seen this Tg by L, it will be lambda square minus lambda square by 2 pi c dB by lambda. If you substitute the value of d lambda by dk through this one, then it is minus lambda square by 2 pi c into d beta by d lambda. So you see it here, it is minus dTg by d lambda. If we substitute it, minus lambda square by 2 pi c minus and if you have to differentiate these ones again with respect to lambda. So once you can consider d beta by d lambda constant and lambda variations. So so that's why you see it here, L, this L into delta lambda, it is here. So L into delta lambda by 2 pi c, there is a factor constant terms. Now we consider the two functions, lambda square and d beta by d lambda square. So lambda square, if you just differentiate first, then it is 2 lambda into d beta lambda, and next times you differentiate d beta by d lambda, so plus lambda square d2 beta by d lambda 2, right? So this will get it. So this is actually the amount of pulse spread because of the different dispersion effects. But here you see, you are not sure which what is the pulse spread due to intermodal dispersion, what is the pulse spread due to intermodal dispersion. So this is generalized relations, but we can calculate separately the pulse spread due to material dispersion, due to obvious dispersion, and due to intermodal dispersion. So let us see how this pulse spread can be calculated separately. So you see here, it is on it here, pulse spread due to material dispersions. And I told you material dispersion occurs because refractive index, when refractive varies non-linearly within the core of the optical fiber. That is true here. If you see n versus lambda, if you just plot it, it is just like these things. You see, it's for silica. You know, if you class fiber, silicon oxide, if you just consider silica fiber, the refractive index variation is like these things. You see it here. It is non-linear, very non-linear, 1.5 to 1.54. It varies, and you see how it is non-linearly varying, right? Or non-linearly varying for silicon oxide. This curve is there. If Geyser, you can see it, right? So it is varies non-linearly. So you see, and since the pulse spread it depends upon the spectral width, so more dispersion effect will be there for incoherent sources like for LED, light emitting diode. But for laser diode, delta lambda is very narrow. On delta lambda narrow in this case, it is in this case 1 to 2 nanometers. In this case, it may be 40 to 100 nanometers, right? So if the delta lambda is very narrow, around 1 to 2 nanometers, then the dispersion will be very, very less, right? Anyway, let us try to calculate this pulse spread due to material dispersion. So from the previous definition of group delay per unit length that you have seen is Tg by L, that is minus lambda square by 2 pi c d beta by d lambda. You see it here. Just now we have seen it. From the definition of group velocity, it comes minus lambda square by 2 pi c d beta by d lambda, group delay per unit length. So we have started with these relations from the depth group velocity. Now the group delay, this is a general. Now group delay due to material dispersion, that times Tg, let us say T mat. Group delay, total group delay will be there over a length L, that will be L by C, you see L by C, lambda square by 2 pi C, d beta by d lambda, right? But now, in case of fiber of refractive index, it is actually co-refractive refractive value to lambda. The n is a function of lambda, so beta is a proportional constant to 2 pi by lambda. K, it is very similar to K, 2 pi by lambda, but in a medium it is 2 beta by lambda times n. Refractive index you have to consider. It's a free space parameter, lambda, but if in a medium it is beta, the 2 pi lambda times n, but now n is a function of lambda. So if you just differentiate d beta by d lambda, you see it here, d beta by d lambda, that is 2 pi by lambda into dn upon d lambda. N function will be, if you dn upon d lambda, that is lambda n, two functions are there. So dn upon d lambda, next times the lambda if you differentiate keeping constant n, so it is minus 2 pi n by lambda square. These simple differentiations. So d beta by d lambda will be replaced by this one, these two terms. So you see it here after simplifications, 2 pi will cancel. You see 2 pi will cancel. So lambda will cancel. One lambda will be there. One lambda will be there, and that lambda, or if you just take common here lambda square, then 2 pi n will be there, and here lambda will be there in the numerator. That's what it is here. It's lambda dn upon d lambda. That is minus plus will be there. It is negative will be there. So these terms will be first terms. The lambda square will cancel. So it is n. I mean lambda square if we take common, 1 by lambda square. So it will be 2 pi n. So n, and that lambda square will cancel here. So it will be n. Simply n will be there. N minus this fact lambda. Lambda square will be multiplied lambda square. Then lambda dn upon d lambda will be there. Lambda dn upon d lambda. It's not too difficult, but this you have to derive it yourself. I mean, it's very easy. Instant maybe okay, for the timing it may be you can skip it this derivation, but in the end it may be asked, so be careful about it. So L by C, n minus lambda dn upon d lambda. So the pulse rate, this is the group delay, but the pulse rate will be when you consider the per-unit wavelength times the total spectral width, dt mat by d lambda times delta lambda. And so again you have to differentiate this factor with respect to lambda. So you see it here, dt mat by d lambda times delta lambda. So L by C, dn upon d lambda, you see it here, n will be differentiating. So with respect to dn upon d lambda, and next two terms are there, two factors are there, two functions are there, lambda, dn upon d lambda. So once you differentiate lambda, it will be 1. So dn upon d lambda. Another case, lambda will be constant, lambda into dt upon d lambda 2. Right. So that's what it is here. Now you see these two terms will cancel, and ultimately we'll get minus lambda dt on lambda 2 times L by C times delta lambda. That's what it is here. You see, minus L by C, L by C lambda d2 n upon d lambda 2 times delta lambda. So this is a factor. This factor you can determine it if you know the n versus lambda for particular materials, right? From the curve you can find out. And delta lambda, this can be obtained from the source statistics. Which source, what is the spectral width, L the distance of propagation, the velocity of light. Generally, this factor is provided. D2n upon d lambda 2 operating wavelengths will be given. So from these factors, you can determine amount of pulse spread in SM fibers due to material dispersion. And if you plot this material dispersion, the negative sign here actually, negative signs you can see it here, and negative signs. It is actually हमको मालूम नहीं, तुम जहां से भी तुम इतना सब लेके आओ, हाँ हाँ टुकड़ा बांधने के लिए। कभी भी जाओ के ले, कभी जब भी फुर्सत आप जाके ले आओ, अभी चाहिए हम जरूर। दशरथ को कितने बार बोले वो नहीं लाया, ड्राइवर को बोल देते हो तुम जाके मैनेज करो, समझे ना, इतने देखो इतना बड़ा. So you see metal dispersions. If you just plotted this metal, this is the amount of pulse spread due to metal dispersions. And if you just plot it, the metal dispersion versus lambda, you can see it here. Negative sense. Negative sense actually, it is actually comparable. I mean, it is a difference among the group velocities. So one can be more, one can be less, like these things. And that's why negative will be there. But it can be sometimes positive, sometimes it can be negatives, right? So you can see it here, the amount of pulse spread, it is for silica, generally it is silica, it crosses at 1.27 microns cross x-axis. So 1.27. Meaning of it, that means at this particular wavelength, this metal dispersion is 0. But so if you choose the wavelength at this particular wavelength, then there will be no metal dispersion. But that is generally impossible. There is no such source that exactly will emit this 1.27 microns, right? Even if you have a laser source, very difficult to get exactly this wavelength. Some variation always will be there. So always some metal, it is inherent, metal dispersion would be there. But this dispersion can be minimized if you consider very narrow or spectral width. Also, if you choose the lambda in the longer wavelength side, I mean, around in these regions, then a longer wavelength side, that is metal dispersion or this factor minimum, then n versus lambda factor minimum, then I mean D2 this factor minimum, then you can minimize the metal dispersions. Okay, this is about metal dispersion. Next, you consider the waveguide dispersion. Waveguide dispersion, we have seen this, that because 80%, 20% power flow in the core and in the clad, right? And that times beta is a function of n by lambda. This is n by refractive index by lambda. Waveguide dispersion calculation is difficult in the sense that because n is a function of lambda, so if both the separately is difficult. Because if you calculate the metal waveguide dispersion, the metal dispersion always will be there. So n versus lambda, it will be that variation will be there always. Because for all the medium is not ideal mediums, some variation always will be there. But if you assume the cladding is independent, cladding refractive index is independent of lambda, right? And all the expressions are expressed in terms of N2, not N1, then you can calculate the waveguide dispersion alone. Otherwise, if you calculate the distance, metal dispersion effect always would be there. Metal dispersion effect can be neglected if you consider n is independent of lambda. So core it always will be there, but if in the cladding regions, you can assume it because very small power is flowing in the cladding, and so in that case, if you assume this cladding refractive index is independent of lambda, and all the relations if you express in terms of N2, then you can calculate the pulse spread due to waveguide dispersion only. Right. So in this case, all the relations will be in terms of N2. You can see it. You can see it here. Now remember, BV normalized propagation constant. We have seen this gamma square A square upon V square. Mu square A square upon V square. We have seen it. So from that, just a minute, and let me check it in what is that relations. We have derived earlier normalized propagation constant. We have defined normalized propagation constant. Just a minute. Beta B A square W not comma W, it is actually rectangular plane systems. It is W and W square A square upon V square, right? That we have seen it, right? W. So from that relations you can have it. You have seen these relations earlier. Beta square K square minus N2 square N1 square minus N2 square. And since N1 N2 difference is very small, so these relations will be considered as beta by Nk minus N2 by N1 minus N2. I told you one variation, it is, you see the N1 to N2 variation 1.5 to 1.447. So only 0.01 variation is there, right? So you can consider this one. So now if you consider this one, then beta, proportional constant beta, you see it can be expressed as N2K. You just simplify it, it will be N2K into 1 plus B delta. B is the normalized proportional constant. Beta equal proportional constant equal to N2K into 1 plus B delta. Right. Next, you see, so object dispersions due to group delay due to object dispersion DWG. It will be from the definition we have seen is L by C d beta by dk. Now, not in terms of lambda, in terms of k only we are writing it. So it is L by C d beta upon dk. Then you see it will be L by C beta. Just now I have seen is we have seen it beta. It is N2K B delta, right? So if we just differentiate it with respect to K, then it comes L by C N2 plus N2 delta D of KB by DK, right? Since beta equal to this one we have seen last time, you see it here, same thing I have differentiated d beta by dk, that is into K equal to 1. And next time there is KB, if you consider the N2 delta is the constant terms, KB is the variation parameters. So d of kb by dk, right? That's why it is come. It comes this one. So the pulse spread, this is the delay due to object dispersion. The pulse amount of pulse spread. So you have to difference with respect to lambda times the spectral width you have to consider. So that is dwj by d lambda times delta lambda. So you see. So these expressions again you will differentiate with respect to lambda, right? In this connection also, these expressions can be expressed in terms of V number. You see it here. How KB is replaced by V? V it is actually K V number. We have seen it KAN numerical aperture. Now KA numerical aperture N1 root over 2 delta. I just now I have mentioned N1 N2. They are almost similar. Very small differences here. So N1 is now replaced by N2. I told you why N2, because you have assumed N2 is independent of lambda. So it is Ka N2 root over 2 delta. And if you just differentiate with respect to with respect to dV by dk, right? dV by dk, then it will be this factor, right? dV by dk. So this actually can be written as this d of kb by dk. That is actually d of kb by dv into dv by dk, right? And Ka can be replaced by K equal to actually V by this factor. So if you consider all those things, just simplifications, you will get these ones. It will be in terms of the group delay due to object dispersion will be simply K will be replaced by V, right? Because this is the constant factors. They are the constant factors, say K times C dash. If you write V equal to K times C dash, and then K equal to V by C dash, and if you differentiate dV by dk, that is C dash. So ultimately it will be same as this, only K will be replaced by V. Because you see generally the factor actually we'll see it why it is in terms of V, because for a particular materials generally some factors are available, say d2VV by d lambda, this type of factors are available. So anyway, if you get this delay as a delay due to object dispersion is this one, then you can find out amount of pulse spread. The pulse spread will be always per unit wavelength times the source spectral width. So dTWG by d lambda times delta lambda. So again you have to differentiate this one with respect to lambda and multiply by lambda, you'll get the amount of pulse spread, right? But while differentiating these ones, you see, you can consider this one. Initially, it will be dd lambda of whole things will be there. So first term will be 0. N2 is independent of lambda, it will be 0. This will be there. And so here it will be d of VB by d lambda, dd lambda into dd lambda of this one whole things. Again, this can be considered dVB by d by dVB. Actually, here it is it d by d lambda into dVB into d lambda by dV. Same thing can be written it here, and dVB by dV. Actually, you want to calculate this in terms of lambda. So d lambda by dV can be calculated from these relations k equal to 2 pi by lambda. You see it k equal to 2 pi by lambda. So dv by d lambda or d lambda by dv, you can calculate it from this one. So after substituting all these things, what you'll get it? You'll get that TWG. It is not written here. So I'm writing the final expressions actually here. It will be L times delta into N2 times C. C. Let me check it. If we just substitute all those things, you'll get the C into L delta into delta lambda will be there into delta lambda into C by lambda. You'll get it. This is the expressions. L into delta into N1 minus N2 upon N2 and repetiveness of the core into a spectral width will be there, and to C times lambda again and times V into D2 VB by 2. This factor. This factor actually, this factor generally it is available for particular materials, right? So if you know these factors, then you can calculate the waveguide dispersions, right? So these are given in Kaiser, you can see it, right? So you can also, from these two expressions, you can compare the waveguide dispersion with the material dispersions, right? The two expressions can be compared, right? And if you just plot it, this waveguide dispersion, waveguide material dispersion, the material dispersion, you have seen it is at 1.27, it is 0, and next it is increasing, they are also increasing. But waveguide dispersion, you see it here, it is in this nature, right? It is in this nature, waveguide dispersions. So this is waveguide. Waveguide dispersions, waveguide dispersions. And interestingly, you see, if these two dispersion are compensated, generally it is compensated at 1.55 microns. You see 1.55 microns, then this will be cancelled by the waveguide dispersion. They are opposite in natures, right? From the curves, you see at this point, exactly opposite in nature. That's why if you can maintain the wavelength at 1.55 microns, then the dispersion effect would be minimum, right? And if that is the case, that fiber is called the dispersion shifted fiber, DSF fiber, dispersion shifted fiber. And this, of course, material dispersion will be, you see, it material dispersion, it is compensated by the waveguide dispersions, right? Right. So that is dispersion shifted fiber. Another fiber is also there, that is dispersion flattened fiber, where you see where here a particular wavelength dispersion is minimum, but dispersion flattened fiber, a certain region is there where dispersion effect is minimum. That is dispersion flattened fiber. We'll see it how it can be designed. So this is the waveguide dispersion, material dispersions. One more dispersion effect is that is intermodal dispersion, that is in fiber. In fiber, you see, I told you many modes will be there, and these modes they will travel with different velocities, so they will arrive at different instant times. So because of these things, pulse plotting will be result. You think about in a ground, say 10 players are running, there will have different velocities. They will have arrive at different instant times. So if you plot that the time arrival times, then it will be broadened. Right. So here you see, even in the ray optics, if you just consider, you see, you can have rays that follows the axis. You can have rays that have the angle with the axis. So maximum distance will be traveled by the ray with the that follows the, I mean, critical angles at this point, almost less than just critical angles, right? From this side, if you just consider, then so maximum distance will travel by these things. Travel by this you can say marginal ray. This is called the axial ray. So the distance will be different for the axial ray and axial ray and marginal ray. So accordingly, intermodal dispersion effect will be occurring. Right. So let us try to calculate here. We can calculate if you calculate the time difference, that will give the value of time difference. Delay actually, these things are in time unit. So time difference will be the intermodal dispersion. That means Tmax minus T minimum. If you just calculate T max minus T minimum. That will give the internal dispersion effect. What is T max? The time taken by the marginal ray to cross a particular fiber length. And T minimum, that is the time taken by the axial ray that follows the axis. So here I'm just taking 1 minute to 2 minutes now to calculate this one. So you see it here, just consider two lengths. This is suppose a triangle. If you just consider here, this from the geometry you can calculate. There's no need of this wave guide here. A simple just I mean mode optics or wave theory is simple geometrical optics. You can use it here. So you see that this is the L1. This length is L1 and this length is L2, right? Then if you calculate L2 minus L1, that is the difference of length. That is difference in length propagated by the marginal ray and the axial ray. That is L2 minus L1. Now this L2 minus this is 90 degree, right? This is 90 degree, and this is actually this corresponds to critical angles, right? Theta C. So you can write L2 actually L1. See L1, and if you see it here from the geometry, L2 by L1, you see L2 by L2 by sine 90 degree, it will be L1 by sine theta C. So L2 by 1 sine 90 is 1. L2 you see this by this angles equal to this angle by this length by these angles from the trigonometric relations. So L2 by 1 equal to L1 by sin theta C. That means L1 into N2 by N1. That means L1 N1 by N2. So if you just put L2 equal to this one, so L2 equal to L1 N1 upon N2 minus L1 and take common, you will get this L1 into delta. Actually, delta actually here it is, you know, N1 minus N2 upon N1. But since they are very small, we are replacing N1 by N2. But approximately you can consider it. So it comes delta L equal to L1 into delta and delta L. Right, L into delta, and so T max minus T minimum. So delta L, so delta T is equal to Vt. So in that case, C into T, that is delta, and into refractive index you have to consider refractive index delta L to N's. So that is actually N1 delta. Just now I have seen it. N1 delta. This delta L into N1 into C. And delta L, we have seen this just now, L1 into delta, right? So that is L1, just now we have seen it, L1 delta, that is L actually, if for certain length L. So L delta N upon C. So the delta T actually time difference. So if you consider certain length, so actually it is T max minus T minimum, actually N1 delta L upon C. That is the intermolar dispersion in MM fibers, MM fiber. Okay. I'm stopping these ones. If you have any questions, quickly can ask. For any expressions, any concept, if you ask, you please ask. Any questions? Anybody? Any relations? Anything? Quickly. I'll stop it. Anybody? Any relations? Also, but then and others.
Sir.
Any questions? Yes.
No,
Any
sir.
questions? Anybody else? Any questions? People are not asking anything. Any surprising. These expressions are most important from in some point of view, and also for conceptualizing most important from quiz point of view. So take care of all these things. If you don't have any questions, I'll stop it. Anybody else? Any questions? Whether others are listening or not listening, questionable. Anyway, see. So many persons are there, but no one is asking. Naman, Rishabh, are you present, people? Vinamra, Ayush, or are you sleeping, you people? Or you have left the mobiles or someone else? Someone here you are, you people. Priyanks, Rohan,